Okay, good morning, everyone. So we've been talking about interactions of electromagnetic waves with electronic states. Okay, and last time we talked about the electric dipole approximation and started to talk about what happens when you go beyond the electric dipole approximation. Okay, so beyond the E1, which is electric dipole jargon approximation. And so when we do that, what we're really doing is we're expanding the factor of e to the I k dot position operator that occurs in the matrix elements that we're interested in for small k. So actually, at the end of today, we'll talk about a situation where that doesn't work very well. But for right now, that's the expansion we're going to have in mind. So the operator that occurs in matrix elements is the dot product of the polarization of the wave with an operator that's acting on the electronic states. And when you expand that out, the first term is the dipole term, which is just proportional to the momentum. And then the second term you get combines two things that are proportional to the magnetic field. And that is the spin, or sorry, the orbital angular momentum, and it turns out twice the spin. They come in that linear combination. Okay, and this k hat cross polarization is the direction of the B field, the magnetic field of a wave, of a plane wave. So that's certainly going to be associated with the magnetic field of the wave. And then the next term in the expansion looks like this. It's got dot products of both the propagation direction and the polarization direction with both the momentum of the electronic state and the position of the electron. Okay, and then this goes on forever. And this is associated with a tensor because it depends on two different indices. One index for the momentum and one index for the position. So the way we write this is our perturbation. So when we did time-dependent perturbation theory, we broke down our operator into v times e to the I omega t and v dagger e to the minus I omega t. And that v we're expanding as a electric dipole part plus a magnetic dipole part. That's the term with the direction of the B wave in it. And then an electric quadrupole term. And we'll talk later about what happens when you keep going. So this is magnetic dipole. And E2 is just jargon for electric quadrupole. Okay, and so when we do an M1 transition, what we're really doing is we're taking the matrix element that is supposed to go into the rate or the cross section that we found, squared. Okay, and the fact that we're squaring it means we don't care about that factor of I. And so we get omega squared over 4c squared f k hat cross polarization dotted into L plus 2s initial state. So one thing that you should be suspicious about at this point is, wait a minute, why did I just isolate that one term? Why didn't I include this and this? Because then when I compute the matrix element squared, I might get cross terms where this is multiplied by that. And so the answer is because selection rules actually help us out here, because the selection rules for a magnetic dipole are completely different from electric dipole. And so in fact, they can't contribute at the same time. It's always one or the other. So let's see how that works. So first of all, what do these L and S operators do? If you're acting on a state that's an eigenstate of angular momentum, they can't change the total L or the total S, because when you act with L, the operator, it just moves you around without changing in the L space or the S space without changing them. So these things don't change. So they not only don't change L and S, they don't change the principal quantum number either, the thing associated with radial excitations of the electronic state if it's in an atom. So they don't change the principal quantum number or the total orbital angular momentum or the total S. They can and do change M sub L and M sub S. By 1 unit. Oops. So remember, last time we said that the electric dipole operator always changes L by 1 unit. This one never changes L by 1 unit. And that's why when you're computing this matrix element, it's one or the other. You can't have both E1 and M1. So in fact, summarizing what we just said in words, here are the magnetic dipole or M1 selection rules. This is for single electron transitions. So for example, this would apply in the hydrogen atom. It would also apply in a more complicated atom, as long as your transition of your atomic state is just moving one electron from one orbital to another, right? So in that case, the principal quantum number doesn't change. The orbital angular momentum doesn't change. The M component can change, but only by 0 or plus or minus 1. Because if you look at how the operator, so the S operator isn't going to change M sub L, and the L operator can, but it always changes it by 1 unit or 0 units. And the same thing for the spin. So the Z component of spin can change by 0 units. For example, if this L part is contributing, that would change the spin by 0 units. And if this spin part is contributing, then it can change it by 1 unit. So this can be plus or minus 1. Now, as a corollary of that, and this is often what one uses in practice, if delta L is 0, if the orbital angular momentum doesn't change, then that means that the parity of the final state is equal to the parity of the initial state, because parity is minus 1 to the L. So if L isn't changing, then neither is the parity. So that's for single electron transitions. And then you can talk about multi-electron transitions. So we just have one photon still, but it's moving the electrons around more than one at a time. There's no reason why it can't do that. Especially because in an atom, the electrons are coupled together by the spin-orbit interactions and by the Coulomb interactions. But it's still going to be true that the parity doesn't change. So you have this parity selection rule, and the reason for that is just that the parity of this operator is +1. So one way of thinking about that is when I flip parity, or when I do the flip of the coordinate system in parity, the position coordinate flips and the momentum flips, and L is equal to momentum cross position. And so I get 2 flips, which is +1. So this operator does not change parity. And so if my initial state has some parity and I don't change it, then it will have to match up with the final state with the same parity. So that's true. And then the change in the total angular momentum has to be 0 or ±1. The change in the z component is also 0 ±1. And then we had the selection rule last time that we talked about, where it's always true that the sum of the total angular momenta has to be non-zero or is greater than 0. So this is always true. Okay, and then also if you work out the consequences of this operator within the Russell-Saunders approximation, so to the extent that the Russell-Saunders or LS coupling scheme is valid, which remember is not exact when the atomic number is very large, then you don't change L and you don't change S. And again, it's for the same reason that we've been talking about. Okay, so as I've already mentioned, but we'll say it here officially, you cannot have both electric dipole and magnetic dipole for the same transition. That's really the reason we're allowed to do this expansion and pretend that it's, well, not pretend, it is one or the other. Okay, and the easiest way to see that is just look at the parity selection rule. For E1, electric dipole always changes parity, and magnetic dipole never changes parity. Parity of the final state is always equal to the parity of the initial state. And so that's all you have to know that they can't, for a given transition, they can't both contribute. Okay, so in fact, the 21 centimeter line, which we've talked about several times, is what's called an M1 transition. Okay, it doesn't change the principal quantum number. Remember, it's a transition between the n equals 1, the two n equals 1 states of hydrogen, so it's not changing n, and it's not changing L, but it is changing the spin. It's a spin flip, is what it's doing. So it comes from specifically this part, the magnetic field of the wave dotted into the spin, the electron spin of the electron in the atom. Okay, so this is the B field, and this can change spin. And specifically, it changes the Z component of the spin, of the electron spin, we should say. Okay, so what that means is the 21 centimeter line is relatively weak because every time you expand further in the expansion we're doing, it gets smaller in the long wavelength limit. And the 21 centimeter line is 21 centimeters is extremely long compared to the size of atoms. So the long wavelength expansion that we've been doing is a very good one. Okay, so let's now go on and talk about the E2 or quadrupole. electric quadrupole transitions. Okay, and so if you look at that term in the expansion of the perturbation, it looks like this. It turns out you can write it as a commutator. And this is very much like how we wrote the electric dipole as a commutator. It turns out it's the commutator of the H0 Hamiltonian, specifically the p squared over 2m part of it, with the following operator. So there's a k hat dot r and an e hat dot r. So I'm just telling you that you can work out the details, or they're in the notes, but it's not too hard to show that that's true. What I do want to emphasize is, why is this a good idea to write it this way? For two reasons. One is we got rid of the momentum part of it. So the momentum operator was there when we originally wrote down the VE2, but by writing it as a commutator, we got rid of it. And then therefore, when we evaluate a matrix element for a real atomic system, we don't have to worry about taking derivatives of the wave functions, which can be relatively painful. But even better is that now if we wrote it in terms of H0, when we put this in a matrix element, either this H0 can act on the left on the final state, or when it's the other term in the commutator, it can act to the right on the initial state. And you see those contribute with a minus sign. So that means this can be replaced by up to a minus sign, E initial minus E final, which is going to be h bar omega. Right, so now we can just take away the commutator and write h bar omega times this operator. And so it's useful when doing this to define, this is how it gets its name, to define the quadrupole moment tensor. For which I'm going to write the letter Q. So it's defined like this. In terms of the position operator, it's Ri Rj minus R squared over 3 delta Ij. This is for I and j equals x, y, and z. And so if I write that, it's got two indices, just like a matrix, and so I can write it. Sometimes we put a double harpoon on it to distinguish it from a vector. And if we write this as a matrix of operators, it looks like this. So there's 2x squared minus y squared minus z squared over 3. So what did I do here? I just took this, and that's equal to x squared when I and j are both equal to x, minus 1/3 x squared plus y squared plus z squared. Okay, and the other things on the diagonal look similar. So this is 2y squared minus x squared minus z squared over 3, and then 2z squared minus x squared minus y squared over 3. And then everywhere off the diagonal, because delta ij is the identity matrix, I just get x and y, for example, here, and x and z, and y and z. And the way it's constructed, it's symmetric. So it looks like this. Okay, and so written as a matrix, this is a traceless symmetric rank 2, just because it has two indices, tensor. The rank is just equal to the number of indices here. So ordinary vectors are rank 1 tensors. So the nice thing about writing it this way is then we have a compact way of writing our perturbation. So I've taken away the commutator at the price of putting in a factor of omega, actually h bar omega, but that kills the h bar in the denominator, divided by 4 times the speed of light. And then I have a dot product of this tensor sandwiched in between the direction of the wave and its polarization. So when you see a dot product of a double harpoon thing like that, that means you just multiply this just like it was a matrix. In fact, it is a matrix. But it's not just a matrix, it's a tensor. Okay, and then we're going to use that operator in matrix elements. And I'm not going to bother to try to write out all the constants that go with it, but basically you have final state, you put that operator in there with some appropriate constants, initial state. And so now we can work out, because we know what the Q operator looks like, we can work out the selection rules. Okay, so let's do that. The most basic one and the easiest one is that it has parity +1. So I'll write the parity of the E2 operator is +1. And so all we need to do to know that is just to stare at each term here. If x flips in sign and y flips in sign, then xy doesn't flip in sign. And you notice everything here is quadratic in the coordinates, all of these terms. And so all of them, when I flip each coordinate, they don't change sign, which is another way of saying the parity is +1 and not -1. So that means if we know the parity of the operator, we know the parity of the selection rule. That means the initial state and the final state have to have the same parity, otherwise you get 0 for the contribution. Okay, what else can we say about the operator Q? It changes, for example, M sub L by 0, 1, or 2 units. So how do we know that? We know that because, again, if I look at any component of this matrix, each x, y, or z can have an e to the I phi in it or an e to the minus I phi, and there are 2 of them. So no matter what combination I look at in there, at the most, it's going to have an e to the 2 I phi or e to the minus 2 I phi. And so when I do the integral, I'm going to get 0 unless the initial and final states match that. So this is just because Q has e to the 2 I phi's, e to the I phi's, 1's, e to the minus I phi's, and e to the minus 2 I phi's. So you can only change M sub L by 0, 1, or 2 units, and then you can convince yourself that similarly, you can only change L itself by 0 or 2 units. So one way of thinking about that is each coordinate basically changes the orbital angular momentum by 1 unit. We already saw that from when we were talking about the E1 transition, but here you're always doing it twice. Every term here, you're doing 2 of these. And so you can change it by 1 unit up or 1 unit down, but then you change it 1 unit up or 1 unit down from that. So you can't change L by an odd number, but you can change it by 0 or 2. Okay, and then finally, an obvious thing is that nothing here involves spin, and therefore the spin won't change. So we already know that total spin doesn't change. That's always true. Spin is intrinsic angular momentum, which is another way of saying it never changes for a single electron. So M sub S changes by 0 units for an electric quadrupole transition. So when I was saying spin, again, I was saying spin for a single electron, but if my transition involves multiple electrons, then that may or may not be true. So to say that another way, if only one electron is changing states, then delta L is 0 plus or minus 2. Delta M sub L is 0 plus or minus 1 or plus or minus 2. Delta M sub S is 0. Okay, and then parity is not changed. Those are the selection rules. But that last one actually is redundant with this one, because again, parity is just minus 1 to the L. Okay, so that's if one electron is involved. If you have multiple electrons involved, so for example, in helium, you could have both electrons change states, then it's still true by the same exact argument that the parity can't change. So the product of parities is plus 1. But now I can rearrange the angular momenta a little bit, but the total change is still less than 2 or less than or equal to 2. No matter what I do, I can't change the z component by more than 2. And then it turns out that the sum of the two total angular momenta, instead of being greater than 0, is now greater than 1. So for the LS coupling scheme in particular, again, nothing, the total spin doesn't change, just because our operator didn't involve spin at all, and the total orbital angular momentum can be anything as long as it's not bigger than 2. Okay, so those are the electric quadrupole transition selection rules. And one immediate consequence of this is you cannot have both E1 and E2 for the same transition. So the reason that's immediate is you just look at parity. Excuse me. So the parity for E1 was it always flipped. And here, just like for magnetic dipole, the parity never flips. And so they can never happen at the same time. And that's why there's never any interference in that expansion that we're doing. Now you can have magnetic dipole and electric quadrupole for the same transition, because they both don't change parity. But E2 allows more transitions than M1 does. So if they're both allowed, then there might be a competition, or it might even be a mixture between magnetic dipole and electric quadrupole. But then there are some transitions where it's only electric quadrupole that can contribute. This is less constrained. So just for example, I could change the angular momentum by 2 units, which magnetic dipole can't do. Okay, so now this explains, by the way, why we spent time learning how to figure out what the spectroscopic term notations were, first for the hydrogen atom, then for helium, and then for more general atoms, is because now we can apply these rules. If we have some excited state, for example, and we want to know what is it going to decay into, what lower state will it transition to, we can get that by applying these rules and figuring out what's the first term in the expansion that allows it. And in fact, if we continue that, so continue multipole expansion, of our perturbation. Remember, our perturbation looks like this. It's e to the I k dot r, polarization vector dotted into momentum minus I k cross s. And so you're just expanding that in small k. And we're not going to do the expansion, but we'll at least say what the names of the things you get are. They are electric and magnetic Q, where Q can be 1, 2, 3, 4, etc. And so, for example, E3 would be electric octopole, and M2 would be magnetic quadrupole. It involves the magnetic field of the wave interacting both with the spin and orbital angular momentum. And then you can see the pattern of how the parity goes. The product of the parities has to be -1 to the Q if it's an electric Q transition, and it has to be the opposite if it's a magnetic Q transition for each of those Qs. And then the change in angular momentum has to obey this rule. This is a triangle rule. And so really what that rule is reflecting is the fact that the EQ or MQ operator, when you work it out, is carrying a certain amount of angular momentum. And that angular momentum is really just h bar times q. And so by addition of angular momentum, this is really, I can rewrite this as J initial minus J final in absolute value. So it's just saying that I'm either adding h bar up to h bar q or subtracting h bar q from the initial state to get to the final state. Okay, and then similarly for the change in the z component, that has to be less than or equal to q. These rules are for both EQ and MQ. Okay, and so if you're trying to figure out what transition occurs between two atomic states, you look at the selection rules and the one with the lowest Q wins. So in long wavelength limit, the lowest Q wins. And the lowest Q that allows the transition to occur at all is going to win. And by allows, it just means the selection rules are obeyed. So in particular, when I say lowest Q wins, you might say, well, which Q, EQ or MQ? And the answer is it's always one or the other, just because these two selection rules won't allow both of them to occur at the same time. So whichever Q is the lowest Q will be either electric Q or magnetic Q. Okay, any questions on that before we switch topics slightly? All right, so as mentioned earlier, we're now going to talk about a case where the expansion that we just did doesn't actually work very well. And that's the photoelectric effect. So we're actually going to be dealing with the photoelectric effect as it pertains to atoms. There's also a way of dealing with the photoelectric effect where you don't talk about atomic states. Instead, you talk about, and this is more relevant for the photoelectric effect as originally explained by Einstein, where you talk about electronic states in metals. Okay, it's the same sort of idea, but the way we're going to be doing it is, or the version of it we're going to be doing it is a little bit simpler to calculate is all. And so our version of it is going to be light hits an atom and it ejects an electron. And our goal is to calculate the differential cross-section for that to occur. So that's d sigma by d omega. Omega is d cosine theta d phi. All right, and so to write out in a little bit more detail, the initial state is, we're still going to call it I, but it consists of an atomic bound state plus a photon. So the photon we'll talk about first. It's just going to have energy that we're going to call h bar omega, and polarization, curly E hat, and momentum, which is the energy divided by the speed of light times the direction of propagation. So it looks like that, h bar omega over c times k hat. Okay, and our atomic bound state, we're just going to, for simplicity, we're just going to deal with ground state, the ground state. So this atom sitting in its ground state when it's minding its own business, when it gets hit by this marauding photon that comes along. So that means we're going to write it as if it were a hydrogen atom-like state with some atomic number. Okay, so this is going to be a ground state. In particular, that means the angular momentum and its z component are both 0. We'll write down the wave function for it later, but it's basically just a hydrogen-like state. And there's no reason we can't do this for other states. It would just be a little more complicated. And we're just trying to illustrate the idea here without being too complicated. Okay, and then our final state. Here again, we're going to do something to make it a little easier. I'm going to call it a state capital K vector. And we're going to pretend that it's a momentum eigenstate. And I say pretend because that's never exactly true, because the atom is always, it has a nucleus that's carrying some charge, and if the electron's trying to leave, the nucleus is trying to pull it back, and that will distort its wave function, and so it won't exactly be a momentum eigenstate. So this is an approximation. And we could deal with that approximation by doing it right, but it would just get a lot more complicated. And so we're trying to avoid complications. Okay, so the final state momentum is h bar times the wave vector. And the energy of it, since we're conveniently pretending it's a plane wave, is just h bar squared k squared over twice the mass of the electron. Okay, so with that setup, now let's just think about what we learned from Fermi's golden rule. First of all, there's a delta function in it, which is just telling you energy conservation. Okay, and so what that says is the energy of the photon which is otherwise known as h bar c times little k. Little k is for the photon, big K is for the electron. That energy has to match up with the final state kinetic energy of this plane wave, plus the energy that came from the bound state. So z squared e squared over 2 Bohr radius. Okay, so that has to be true. And so there's a minimum omega that will work, because even if k is 0, which it's going to turn out it can't be, but for our approximation to work, but even if this were 0, this is some constant value, and so omega has to be bigger than what's given by that constant value for this to work. Okay, and so we need, more generally, omega to be larger than some minimum value, because it's going to be h bar, I'm just dividing here by h bar. And when Einstein originally discussed the photoelectric effect on the way to everybody discovering how quantum mechanics worked, that was one of the key observations, is that no matter what the intensity of the light is, if your frequency isn't large enough, or in other words, if your energy isn't large enough, you get no transition. So this has to be true for this to happen. When you're talking about metals, this is not really the energy that's giving you the minimum, but it's the same qualitative idea. Okay, now if this thing is a plane wave, then that means it has to have a pretty strong momentum. Otherwise, the nucleus would be pulling it back and not making it very plane wave-like at all. So that means we're sort of forced by our approximations to work in the limit of large K, which means that the multipole expansion is no good. So we can't really classify this process that we're dealing with as electric dipole or magnetic dipole or anything like that, because it's involving really a linear combination of all of them. We've badly violated the expansion, the multipole expansion. So the reason for this is we wanted to be simple. We wanted the plane wave approximation to be good. And the price that we pay for that simplicity is this won't apply if the momentum is small, which means the wavelength is small. Okay, so what does that mean? That means we have to have h bar squared k squared over twice the mass, has to be much, much larger than the relevant binding energy of our electronic state. Or in other words, we can rearrange this and say that our K has to be much, much larger than Z over the Bohr radius. So just as a check, K wave number has units of 1 over distance. Z is, of course, just an integer. 1 over the Bohr radius is also 1 over distance. So dimensionally, that makes sense. We also want that the energy of our photon has to be much, much larger than z squared e squared over 2a naught. Why is that true? That's true because we've just decided this has to be much larger than that, but this is equal to the sum of them. So that means this has to also be much larger than that. Okay, and we can rewrite that as omega over c much, much larger than z squared fine structure constant over 2 Bohr radius. So here I'm doing some rearranging variables. Just as a reminder, the Bohr radius is h bar squared over the mass times the speed of light squared. And the fine structure constant is e squared over h bar c. So I'm using that to rearrange the constants. Okay, we also had better make sure in our approximation that the velocity of the final state is not too large. Because if it's significant compared to the speed of light, then we should be doing relativistic quantum mechanics, and we're not. So in order for our claim to be valid, that has to be true. And so let's see what that means. That means if I take the momentum divided by the mass, that's h bar capital K over the mass is approximately 2 omega over K. I get that from going back to this equation, where I can neglect this term to first approximation. Okay, and so that gives us that capital K has to be much, much larger than omega over c. Okay, and the main reason that that's useful is that's telling us we can neglect spin. So remember, the term in the perturbation that had spin in it was K cross S, which is omega over c. This is the K of the photon. And so that omega over c we've just learned is small compared to the momentum of the final state. Okay, so we can just ignore the spin, is what this is telling us. And furthermore, if I take these last two boxes, we can combine them into a single box that just says capital K, much, much larger than omega over c, much, much larger than z squared fine structure constant over twice the Bohr radius. That doesn't mean those have to be true in every transition that occurs between electronic states from the photoelectric effect. It just means that for the analysis that we're doing to be correct, it has to be true. All right, so another thing we have to worry about now is the final state wave function. Because it's not normalizable. And so we're going to do a very standard trick to get around that. So what do I mean by saying it's not normalizable? Let's write down a plane wave function. It's got some normalization factor times e to the I k dot r. As the wave function, that's just this thing. Okay, but the problem is if I take the norm of that state, I get infinity. So how are we going to deal with this to make our normalization factor be finite? We are going to put the system in a large box. Of side L. So whenever I say it's large, you get to ask, what does large mean? In this case, large means the size of the box is much, much bigger than the other relevant length scale, the size of the atom. Okay, and so when we do this, which we will commence with next time, we're going to have to check a very important thing, which is if we make our box really, really large, like maybe light years in size, then the answer better not depend on exactly how big we chose it to be. So even though lots of our intermediate steps are going to depend on how big the box is, at the end, we want to check that the final answer doesn't depend on that. Okay, so check later. The answer, and by answer, I mean the differential cross-section, can't depend on L. Even though in intermediate steps, it will depend on L. Okay, so we're out of time today, but next time I think we'll just neatly be able to finish off the photoelectric effect on the last day before the midterm. So as a reminder, there is a midterm on Monday, same room. So this is March 29. My NIU says it's on April 5th. I'm trying to get that changed, but unfortunately I don't have direct control over it. So it's whenever somebody gets to it, it'll hopefully be changed, but ignore the April 5th thing. It's not occurring. And it's going to be based on the last 3 homework sets, 6, 7, and 8. Homework set 8 is due tomorrow. And so on Friday after class, I'll send out the solutions. So you can be up to that amount of time late. So unlike usual, you can't turn this in late because solutions will be going out. And then you can have 2 sheets of paper with any formulas you want, both sides, or 4 sheets one-sided. I will post this to the course webpage sometime later today. And everything else is going to be the same as last time. So bring your own paper if you like your own paper to write with. And so any questions on what will be on the midterm? So it's going to be time-dependent perturbation theory. It's going to be understanding identical particles and how to put electrons into identical particle states and things like that.
Question?
Yes.
Could you just outline what chapters from the notes you'll be on?
I can't do that in real time, but it's basically, if you look at homework set 6, 7, and 8, in each one of them, there's a reading assignment that goes at the top, hopefully. And in any case, it's the material that's covered on homework 6, 7, and 8. I would encourage people when you're studying to not start by studying the notes. It's better to start with the homework problems, look at each homework problem, and then say what concepts and ideas in the notes are related to this, and then go look in the notes from there. Always start with problems. Okay, any other questions on that?
I have one request.
Okay.
Would it be possible to contact facilities to see if they could check the radiator?
I can ask. I think the chances that they'll be able to do anything about that are 0, but we'll see.
Thank you so much. Have a great day.
You too. All right, if there are no other questions, I'll talk to you all on Friday.
Dr. Martin, see you on Friday.
All right.